Okay, so next we will look at one of the most important components associated with the timing in terms of waveforms, what is also called as the transient response. So we have input waveform, we have output waveform. If the x-axis is time and the y-axis is voltage or current, generally these types of waveforms are called as the transient response. And from the transient response we can measure many things that we mentioned earlier, like propagation delay, rise time, fall time, etc. Okay, and this thing is one of the most important things that we will see in this unit also. And let us look at this one simple question that we have here. Draw the response of a RC loop driven by a DC source. So we'll go to this board and try to get a new this thing. Okay, so we have a okay. So we just want to find out what will be the value of the output voltage with respect to time. So if we can just approximate waveforms of voltage versus time, this is T and this is V. Okay. So let's say that this is the output. Okay. So it will look something like this. This is one particular output waveform for some value of R and C. Okay, let's draw a few more. And this is one way it might have gone. Another way is, for example, like this. Another way is even slower. Okay, but one thing is they will all reach the value. Suppose the input is say 2 volts. Okay, this will all reach 2 volts definitely, and each of them is going to take different trajectories depending on the values of R and C. And this is what is very important for our subject also. If the R and C, okay, product is very high, that is if the RC product is very high, then it is probably going to take a long time to reach the output voltage. If the RC product, that is the product of these two numbers, is very low, then it might go up very quickly. And this is also very similar to what happens in digital circuits, where the R and C is again not because of nice resistance and capacitances like these, but these are the parasitic ones that are because of the circuit, because of the wire, etc. And because of that, you will see the delay between the input and the output. It will not follow exactly. Okay, and that is what it's asking here. Draw the response of RC loop. Okay, and another thing is you might have learned in mathematics M1, M2, whenever we have differential equations. Even here for this simple example, you can get a very simple equation, very nice equation, but generally we cannot use for even a simple circuit with say 5 or 10 transistors, which is a very simple circuit. It is not of any almost any practical use in digital circuits. Systems are much larger. We cannot get exact waveforms through analytical evaluation. Okay, that is, we cannot solve an equation for even 10 or 20 transistors and get the output, and we will always use some numerical simulator. Like for example, you've used cadence does not solve any differential equation exactly. Okay, it uses a lot of numerical methods, and the transistor will have a model, and the numerical method will approximate give us a answer to the output, and these models are very good. The numerical methods are very good, so the answer also is of very good quality. But the problem is we cannot do that level of analysis by hand, whether it be two things. One is the symbolic part using differential equations for complicated circuits. We cannot do that. The other thing is the numerical methods. Suppose you say I can do what a computer does, that also we cannot do because it's very complicated, and that's where our hand analysis comes into the picture. A lot of this, what we're going to see in the rest of this unit, is how can we use some approximations to come up with very simple analysis. Okay, that is, we don't need a computer to do that. Well, the answer is not going to be exact. It might be around 80% accurate, but it is good enough for us to get a picture. And that is what we are going to do. How can we get some simpler models for all these complicated resistances, capacitances, etc., for all these timing? How can we get a better, simpler model rather, and that will help us in doing some hand analysis. Okay, so that brings us to the first technical part of this unit, which is what we call as delay models. And these are the ones that we are going to use for hand analysis. And we have considered three different delay models. Delay model is just a way of saying that this is one way to calculate the delay. Okay, so the first one is the RC delay model, and the second one is the Elmore delay model, and the third and final one that we will see in this unit is the linear delay model. So these all will give us some answer for the delay of a circuit. Okay, what is the advantage? We don't need to go to the simulator. I don't need to go to Cadence, open up, create the circuit, do the analysis, right, calculate the waveforms, and then calculate the propagation delay. I can use these much simpler analysis, get the answer by hand itself with a simple calculator, but the answer is not going to be exact. But the advantage of that is relative. Suppose I change something in the circuit, then I can predict whether the delay is going to become better or it's going to become worse. So those type of analysis we can do. Most importantly, like I said before, it will help us do hand analysis. We don't have to worry about creating the circuit, or we don't have to worry about many other things that will complicate the analysis. So the first and the simplest one is the RC delay model, which is going to give us a approximate answer. Slightly better Elmore delay model. A linear delay model has more capabilities, and as we come to each of these models, we will discuss that in more detail also. Okay, so among the first, we will start with the RC delay model. And before we can go to the delay model, we need some simple definitions. Okay, so we have to I'll just come back to this slide later. I want to first look at this transistor definitions. We want the capacitance or the resistance that is associated with the transistor. And if you recall, the transistor is defined in terms of its width and length, the size of a transistor. And these width and length are obviously not constant forever. Width and length will have some particular values, okay, sizes, and it depends on a very important parameter called as technology. And these numbers are very important for us, and we have to look at everything in terms of technology, and that makes it a little difficult because if I write down some design in terms of the technology that we're using today, and if someone picks up this design a couple of years later when the technology has changed, numbers are not going to be the same. So we use a convenient notation which is called as lambda based design rules. and we use these design rules for most of the things that we do. And we are also going to define the resistance and capacitance in terms of this lambda. Okay, and the advantage of doing that, like I just said, is we don't have to worry about very uh, low level details like nanometer size, etc., but we can look at a little bit higher level, and it will also scale up to future technology if we do the analysis in terms of these lambda based sizes. So the first thing, okay, and this is very important, we have two types of transistors. We have a NMOS transistor, we have a PMOS transistor. So first let's look at the NMOS transistor. Okay, so we just draw a simple NMOS transistor, and what is the resistance and capacitance that is associated with this transistor? That is the thing that we are trying to answer. Okay, and we cannot answer that directly. Obviously, we have to look at the size of the transistor, and the size of any transistor from now onwards we are going to write in terms of its W by L ratio, and we will write this number here. Okay, so W by L ratio, for example, might be 2, it might be 4, whatever it is, we will write that here. Okay, now the first thing, this we have to remember this because it's a definition. By definition, okay, for a NMOS transistor with W by L ratio equal to 1, okay, we are going to define that it has some resistance R, and we don't know what this R is because this W by L is in terms of just abstract numbers, it's a ratio. But once we come to a particular technology, whoever is responsible for the fabrication, they will give us these numbers. So then we can back annotate and get the actual numbers for R and C and the delay, etc. But until we do that, we don't have to worry about that. And we can just abstract it to some variables. So we are defining for ourselves NMOS transistor. Okay, if its W by L equal to 1, it is going to have a resistance R. And the same NMOS transistor with W by L equal to 1 is going to have a capacitance that is C. Okay, so you can call this as 1R and 1C. Okay, or just R and C, that is up to you, just to make it simpler, 1R and 1C. And this is the resistance and capacitance that is associated with this particular transistor of some size W by L equal to 1. This is very important. Okay, and obviously we're going to see how this changes. This is the definition. Everything else is going to be related to this particular definition. How it is related, we are going to see. So this thing we will remember first. Okay, NMOS transistor, resistance R. Now the other transistor, based on this definition itself, okay, we have one more transistor, which is the PMOS transistor. So we have to also see PMOS transistor. We don't want to redefine. Okay, we have the same definition, so I will draw a PMOS transistor, and for this PMOS transistor, which also has W by L equal to 1. Okay, so this is a PMOS transistor, W by L equal to 1. Now for this transistor, how much resistance, how much capacitance? That is the thing that we point. And we already have one definition that we have used for a NMOS transistor with the same size, exact same size. The resistance is 1 unit, capacitance is also 1 unit. For a PMOS transistor, okay, we are going to say that the resistance is 2R, the same size. Size is not changing. The exact same size transistor, the PMOS transistor will have a resistance of 2R. That is, the R is the same. Okay, it might be something like 1 kilo ohm or 10 kilo ohm or whatever. If there it is 1 kilo ohm, here it becomes 2 kilo ohm. And the capacitance is going to be the same value. If it is 10 femtofarads in the NMOS transistor, it is going to be 10 femtofarads in the PMOS transistor also. And this is something that we have derived from the definition for the NMOS transistor. How did we derive this? This is a question that you can ask yourself. Okay, so we will stop here for a few minutes.